Hi, I'm Anders Langlands, and Owen, Luke, and I are going to take you through why we're excited about the Rust programming language for writing visual effects tools, and the efforts of the ASWF Rust Working Group to provide bindings for the entire visual effects software stack. Rust is an open source, multi-paradigm systems programming language. All development happens entirely in the open on GitHub, with the direction of the language being decided by RFC process, which means you can follow along with the development and also contribute to the discussion and design of the language easily if you're so inclined. Rust is mostly imperative like C++ or Python, but it's expression based. It also takes a lot of inspiration from functional languages like Haskell and OCaml, with its trait system, its focus on algebraic data types, and lazy range iteration. And by systems programming language, we mean it is explicitly targeting the same problem space as C and C++, and it's designed to interoperate well with C, so you can use it for everything from low-level kernel modules to web applications. It's also looking likely to be only the second language to be incorporated into the Linux kernel after a glowing review from the lead maintainer, and Google have now contracted the main developer of that work to help push it through. Rust's key three tenets are performance, productivity, and reliability. In most languages, you have to give up one or more of these things in favor of another, while Rust gives you all three. Rust explicitly aims for the same performance class as C++, both in terms of speed and memory usage. In particular, it handles safe memory management without a garbage collector. With its high-level abstractions and type influence, Rust can be as easy to read as Python, and the developers have learned from the mistakes of the past and given Rust first-class tooling, including an integrated build and package management system called Cargo, which also includes testing, benchmarking, and documentation generation. There's also standard tools for code formatting, linting, and language servers for any editor that you want. With its strong expressive type system, including its unique ownership model, Rust can guarantee memory and thread safety at compile time. Now, when we hear safety, we often think about security vulnerabilities, and perhaps you think, well, why does this matter for visual effects? All of our systems are cut off from the internet. It doesn't really matter if our renderer has a buffer overflow vulnerability. What it means is that Rust prevents entire classes of bugs that can cause segfaults or worse. In particular, it means you cannot write any of these. There's no undefined behavior, there's no use after free or null pointer dereferences, and there's no data races. Rust will just refuse to compile them. And it does all of this through the combination of its features, some of my favorites being, first of all, the ownership and borrowing system, which manages the lifetime of all the data and references to it in your program, the wonderfully powerful enums, which are the basis of Rust's error handling system, and traits, which are sort of like C++ concepts or Haskell type classes, and are the basis for interfaces in Rust, as well as constraining generics and marking properties of types. In particular, there's two marker traits called send and sync that encode whether a type is safe to move or share across threads. And it's the combination of those with lifetimes that enables Rust to prove that your program is free of data races at compile time. And now we'll take a look how you can use these features in real-world projects to write more reliable, more performant software more easily.
Hi, I'm Owen. I'm a lead software engineer at Leica, where my focus is mostly web stuff. I spend my time building backend services, single page apps, and everything in between. When we started looking at Rust for backend work in 2017, it had a reputation for being hard to learn, but also particularly well suited for security or performance sensitive work. As a sales pitch, it sounds like you needed to have some great risk in order to offset the large cognitive burden. We didn't especially have any deep security or performance concerns, but the language seemed thoughtfully designed, and after a few small projects, it turned out to be a good fit for the mundane stuff too. I wondered if the initial learning curve was a short-term shock rather than a perpetual cost, and over time this seems to have been true. To this point, most of our backends have been a mix of Python, Scala, and Java. Rust quickly became the preference for folks on my team, and people were especially interested in moving away from the JVM for one reason or another. Python is still in heavy rotation. It's not going anywhere. Still, we favor Rust if there isn't some outside factor giving Python the edge. Usually this comes down to packages being available in Python with no equivalent yet for Rust. As more people in the studio got involved in Rust projects, I started to notice some competitive advantages that didn't relate back to the whole security or performance sales pitch. Mostly this stuff comes back to the type system one way or another. If you like the notion of making illegal states unrepresentable, the type system is great for encoding the rules of a system. In addition to the correctness aspect, types can help to explain or document the designs of your APIs. With the type signatures covering the what, the comments and docs can focus on the why, outlining the larger context. During refactors, in Python, we rely on having great test coverage to identify defects related to signature changes. Failing to maintain coverage or not testing for just the right set of inputs can lead to accidental breakage, only to be discovered later on and often in production. This is sort of like the idea of the butterfly effect, where a butterfly flaps its wings and a hurricane is formed on the other side of the world, seemingly unrelated. With Rust, the compiler raises signature-related problems immediately, flagging any incompatible call sites. This is great for iterating on your own code base, but it also makes chores like upgrading third-party libraries a real breeze. Another advantage we saw was in Rust's approach to error handling. In Python, exceptions will travel up the call stack until you catch them, or sometimes not. In a way, you can think of them as being spring-loaded. Rust uses an enum type called result, which signals either success or failure, depending on which variant you have. By treating errors as values, it means that functions advertise the fact they can fail in their signature. When return values are received at a call site, the caller gets to decide how cautious or brash they want to be when they access that value. In Python, our collective success requires hypervigilance. None values are everywhere. Tony Hoare made the assertion that null references are a billion-dollar mistake, and if you've ever had to rush to fix a bug citing none type has no attribute such and such, you know what I'm talking about. A big reason the odds are stacked against us with Python is you can only handle an exception if you can see it coming, and that's not always easy to do. In Rust, types like result and option, which is a similar concept for nullable values, they make it much harder to gloss over the potential points of failure. These types invite developers to make choices. When folks first come to Rust, they might see result and option as things that get in their way. But having extra visibility in this area can make a big difference. Looking back at errors logged in production over the past few years, we can see a distinct picture. It's hard to compare different services doing different types of work, but we can roughly see the footprint of runtime issues is much smaller in our Rust projects. There are a lot of caveats behind these numbers, but just know the Python service actually had more advantages in this matchup. Here's another two services in case you thought that last slide was a fluke. No totals this time, but the breakdown is similar to the last slide. When it comes to unexpected errors like this, fewer is clearly better. But still, unexpected errors often require developers to context switch so they can investigate. I'd rather keep everyone focused on feature work if I can help it. Overall, the benefits we've seen with adopting Rust at Leica have not been those in the hard technical areas like performance or security, though those are welcome secondary benefits. For us, Rust helps keep our teams stay on the same page when they work through design problems, thanks to the type system. Rust helps our developers identify and address points of failure rather than gloss over them. And Rust helps to reduce maintenance burden thanks to the beautiful compiler feedback. Once you're familiar with the novel aspects of the language, like ownership and lifetimes, the language starts to pay dividends by making it easier to iterate, refactor, or completely redesign over time. Thanks for listening.
Hi, my name is Luke Titley, and I'm extremely excited to talk to you about EEL, a 3D graphics framework that I've been developing. About 6 years ago, I started prototyping a 3D animation framework in C++. From the start, I wanted it to be multi-document and multi-threaded. 2 years ago, I threw the C++ project away and I rewrote the whole thing in Rust, and I'm really pleased that I did. This is what I want to talk to you about today. This is EEL. Although not essential, it can natively wrap USD stages and pass them from one node to another. At its core is an abstraction that defines how to interact with a graph in a multi-threaded environment. Rust is the perfect language for this. In this example, I'm showing a node that contains a dynamic graph of 16 animated characters. These are all loaded via USD scale. This example is fairly conventional. Here, time is transformed by offset nodes that drive animation clips into a skinned skeleton. Skinning is performed on the CPU. Thanks to Rust and its ecosystem, it's trivial to evaluate this graph concurrently and asynchronously. Look at the CPU usage above. EEL is asynchronously caching these 16 characters at 300 to 400 frames per second and using, on average, 70 to 80% of my CPU resources. You can see here playback is at 60 FPS because everything is already uploaded to the GPU. This entire node graph is stored on a property on a node that is itself part of a larger graph. Thanks to Rust, I'm able to build a complex recursive document structure and know that it will behave itself in a threaded environment. Now, look at the same construction, but 1,000 characters. Here I'm caching 2 seconds. You can see my CPUs are at 95 to 100% CPU usage. There is very little contention. Although they're the same asset, I'm not sharing caches or animation data. If I had access to 1,000 distinctly animated characters, the performance would be about the same. This is an 8-core machine with hyperthreading. It's not particularly powerful, but I'm using the hardware that I paid for. So that's a whistle-stop tour of EEL. Let's have a look at some of the internals. So thanks to Rust generics, it's possible to build EEL as a set of completely orthogonal components that can be assembled like Lego. Today I'm going to talk about the compute and caching systems. The compute system is a directed graph composed of nodes with interconnected properties. Thanks to Rust, properties can be any type. EEL isn't constrained to a set of predetermined types. Node property values are computed by one or more ops. An op is a compute function with some additional state. Ops are sorted based on depth in the graph, and this determines the processing order. Ops with the same order can be processed concurrently. Ops can create tasks themselves, which gives us a hierarchy of tasks, and all of that scheduled for compute. A node graph can be packaged inside of a property, which can belong to a node, and this allows us to pass a graph from one node to another. Much like Katana or Houdini lops, the difference is that node graphs can be dynamic. What's passed from node to node is an abstraction. It could be USD, it could be some other geometry processing engine. So how is the asynchronous geometry cache implemented? At a data level, a node graph is a stack of systems. Each system owns a system below it. The base system, for example, stores node property values and connection information. The time system, which manages the geometry cache, forks the systems below it and spawns a new task. Some of the data is shared, topological data like connection information, parenting information. Some of the data is copied, the dense property values that need good cache locality. The fork task computes the results and inserts them into a concurrent hash map. In the end, the fork task terminates, leaving behind the results. So why Rust? You could do this in C++. There's a lot of good reasons for choosing Rust as your programming language for a project, but for me, what tipped the scales was threading. C++ libraries rely on documentation to express what can and can't be accessed concurrently, particularly to avoid unnecessary locks. Thanks to Rust, EEL has that encoded in the API with no runtime cost. Your code, it won't compile if you break the concurrency rules of the API. For example, topological changes to the same graph in EEL cannot be done concurrently. This isn't a massive problem because you can store a graph in a property and properties themselves can be changed concurrently. But I don't need any locks to check that you're breaking the rules. Your code is just not going to compile. Concurrency rules, they're not just about read and write, they're also about how long you spend borrowing data. EEL provides direct access to the memory of property values on a node. This is great. You can directly modify the data in line. If you hold on to that data for too long, though, your code, it won't compile. If you were to guarantee the same degree of safety in C++, you would have to do so with a runtime construct because the compiler isn't doing these checks for you. You'd need more mutexes and more copy and write structures or shared pointers. C++ cannot provide the same safety at the same performance. Although Rust forces concurrency rules to be encoded in your API, you can't know everything at compile time. So the Rust community has a fantastic and rapidly evolving ecosystem of libraries that you can use to build concurrent applications. This is a quick list of the libraries at the heart of EEL. Thanks for listening.
Okay, so Rust's the best thing since sliced bread. But what are some reasons why Rust might not be a good fit for you? Well, Rust has a reputation for having a steep learning curve, and to some extent that's definitely true. Depending on your coding style, it can be hard to learn at first. Writing a program in Rust is definitely a little bit slower to get going than, say, Python. Rust forces you to think about the structure of your program up front and to consider all the possible ways that it might fail. The flip side of this is that what you write is much more likely to do what you intended and to run reliably. Now, people often say that if it compiles, it works, which is obviously overselling it a bit, but it does reflect how it often feels writing Rust. And lastly, it's still a fairly young language. The first stable version was released in 2015. And there are some real best-in-class libraries out there to use, but you're not going to find the same breadth or depth that you would in C++ or Python, particularly for niche domains like visual effects. So that's where we come in. There's already a large collection of battle-tested C++ libraries out there covering a broad swathe of the VFX ecosystem. And we absolutely don't want to rewrite all of this in Rust. We want to be able to use these libraries from Rust to build new tools with where we feel like Rust's features are a good fit. So how do we go about doing that? How do you go about binding C and C++ to Rust? Well, let's consider C first, since it's a lot easier. Telling Rust how to call a C API is a simple matter of declaring the functions in Rust, much the same as you would a C header. And then you can just call those functions directly. Consider this simple function I've got here to write a one-dimensional image. It takes a pointer to a block of pixel data to write, the length of that pixel data, and a code to tell the function what type each pixel actually is behind that void pointer. You can see at the bottom there the transformation to Rust syntax is pretty trivial, and there are tools to do this automatically for you, so linking against the C library is generally as simple as just pointing your build script to it. And what that gives us is by convention called a -syscrate, that is, an unsafe binding to the C library. Just calling C from Rust doesn't magically apply any of Rust's safety rules. And calling this function is still fraught with possible errors. We might pass it a null pointer or a pointer into some random part of memory we don't own. We might pass the wrong length, potentially causing the function to try and read past the end of the pixels buffer. Or we might pass the wrong type for the pixel type code, again potentially causing a buffer overrun. Plus, there's nothing stopping another thread from writing over that pixel data or even freeing it while we're trying to write it to disk. So what we want to do is to build a safe abstraction on top of the raw C calls. For instance, here we might choose to wrap it in a safe function that takes a slice, which is Rust's built-in type that just encodes an array in its length, similar to span. And the slice here is generic over some type T, which implements a trait we've defined called pixel, and we can use that trait to associate the type of the slice with the type code that the C API is expecting, and so keep them in sync. And calling this function that we've made is indeed safe. The pointer we get from the pixel slice is guaranteed by Rust to be valid and non-null, and thanks to Rust's ownership rules, we know at compile time that no other thread is going to be messing around with it behind our back while we're trying to use it. The associated length is guaranteed to be correct, and as long as we specified the pixel type constant correctly, which is done once in the trait implementation I just showed, there's nothing that can go wrong here, at least in the Rust code. Users get a simple API to use where they never have to worry about memory errors or undefined behavior. And the function is easy to use. We just pass it the slice of pixel data, and all of the memory layout shenanigans is handled automatically for us by the type system. Conversely, imagine that we run this program on the bottom and it does segfault. Now we know that the cause has to be that pixel type was specified incorrectly in that trait because Rust guarantees that the other parts are correct. The type system has reduced the space of possible errors so much that we can identify the cause without having to fire up a debugger at all. Now obviously this is a trivial example, but the same thing applies in large programs as well, just scaled up beyond what I can fit on a slide. Rust's type system encodes the invariants that you'd normally have to describe in documentation or in comments in other languages, and it checks them for you so that you can focus on the problem you're trying to solve. Rust helps you create APIs that are ergonomic and easy to use and hard to misuse. And this isn't just chasing some platonic ideal of safety either. It's hard to express how it feels after a little while of writing Rust, just how nice it is to not have to think about any of this stuff. It's like having a weight lifted from your shoulders. As an API author, you can strictly define how the API must be used and have the compiler make sure it's being used correctly. And then you never have to worry about it again. As a user, you never have to worry about whether there's some undocumented assumptions about how you're supposed to use it and whether what you're doing might break now or at some unspecified point in the future. Okay, so C is relatively easy. C++, of course, is a little bit more complicated. Since C is the lowest common denominator, if we want to get at C++ libraries from Rust, we'll have to convert their APIs to C first by writing a wrapper library. Describing the whole process of that would be a much longer talk in and of itself, so I'll just give a brief overview of the main idea here. In any library we want to bind, I'm using iMath as an example here, C++ symbols form a hierarchy. You have one or more enclosing namespaces, inside which you have classes, which themselves contain methods. And the basic idea is we want to flatten that hierarchy in order to get the names of the C functions we want to create to wrap the C++ methods. Now in C we don't have the colons for namespaces, so we'll get rid of those. We also can't have two functions with the same name like these two constructors here, so we'll rename one of them, say to default. C also doesn't support generics, so we'll need to decide what we're replacing those t's with, perhaps floats or integers or both. And then finally, those function names with the types listed out might get a little bit unwieldy if we have multiple template parameters, so let's provide a nice short name for them. And that's the bird's eye view of the transformation that we want to perform. The implementation of these functions just call the original C++ methods, passing through the parameters and converting as necessary. Now, that might seem fairly simple. Of course, it gets a lot more complicated for arbitrary C++, but even if this was all that we were doing, writing all of that out manually would be a colossal RSI-inducing task. So we've written a tool called CPPMM that does all of this for us. It can automatically generate nice, customizable C and Rust bindings to arbitrary C++. CPPMM uses Clang to parse the target library headers, generate an abstract syntax tree out of the target API, and then transform that AST to the equivalent C representation. It then writes out a C library that wraps a C++ library and a Rust-sys crate that calls the C wrapper to get access to the functionality of the target library. The end result is ready to build projects for both C using CMake and Rust using Cargo. And finally, we hand write the safe idiomatic Rust crate on top of these automatically generated parts. Getting CPPMM up and running has been our primary focus up until now, and we've been dogfooding it with examples from our list of target libraries as we go. But we've recently switched gears to actually start building the final bindings and adding features to CPPMM as needed to handle the C++ we find in those libraries. So far, we have a mostly complete safe Rust binding for OpenEXR, and work in progress unsafe bindings for OpenImageIO and OpenColorIO. So we've made a good start, but there's still a lot of work to do. So what's it actually like to use the bindings that we've created? Well, here's the C++ example from the OpenEXR documentation. And here's the equivalent using our automatically generated C99 API. You can see that it's pretty nice, though I've ignored error handling here for the sake of brevity. And you can use this directly from C or from any language that supports C FFI, which of course is basically all of them. The equivalent Rust we'll take a look at in a live coding session I've recorded here. So we'll just create a new binary called demo. We'll cd into there. I know that I've already written some PNG loading code, which will incorporate so that I can load a PNG and output it as an OpenEXR. In order to load a PNG, I need to have a PNG loading crate, which we'll download from crates.io. We'll also grab the pre-release OpenEXR crate, which we've written and published to crates.io. Now, before we do anything else, I'll just run a quick build to build the dependencies, because this is going to build the C++ libraries for iMath and OpenEXR. Then while that's building, we'll just jump over and take a look at docs.rs. So when you push a crate to crates.io, all the documentation is automatically built and published to docs.rs. So you've got all the documentation for every library that Rust has available on crates.io, all in one place, all formatted the same. And the Rust community places a lot of emphasis on having high quality documentation, and in the Rust Working Group we're taking that very seriously as well. So you can see here we've got a landing page with some code examples and a basic instruction on how to build the library and use all of its features. I can search in here, so for instance we're going to need to use RGB output file for the demo that we're doing here, so you can find that. You can see again we've got a simple code example here, and all of the types are all interlinked, so I can see what we have available for the header type, which we might want to use as well. Another fun thing that I've done is converted all of the long form documentation that you find as PDFs on the OpenEXR website to Markdown, which is a format that RustDoc is expecting. And so now all of the type names and everything are all cross-linked to the API documentation as you're reading through those long form docs, which is really cool. As well, all of the inline code examples are now tested as part of the Cargo test suite, so that we can guarantee that those examples are going to stay up to date as the library underneath changes, which is awesome. So we'll just jump in and start coding. I'll need to add the PNG code that I brought in before. We'll also use the prelude from OpenEXR, which brings in all the most commonly used types, as well as I'll bring in the error type, because I know that we'll need that. Then we can just load the pixel data from the PNG that we copied before. Rust Analyzer adds the import for us, which is nice. Then we'll create a file object for which we'll use RGBA output file. We'll use the with dimensions constructor, which just takes the output path along with the width and the height. And we will then just write the pixels out. So we'll pass a reference to the pixels array. I know that the array is densely packed, so we'll use an X stride of 1. We'll use the width for the Y stride, and we're going to write all of the scan lines. This question mark operator here is just Rust's way of passing any errors that we encounter back up the stack. In the case of the main function, I need to change the signature so that it actually returns a Rust result, and that will just convert the result into a standard error code. So if everything's okay, we get to the end of the function down here and we return okay, then that will just return 0 or a non-zero code otherwise. Okay, so no errors from Rust Analyzer. Looks like everything's good. We'll jump back out of there and we'll cargo run, and we should find that we've written out an EXR file. There it is. And so now I can just read that, and there it is. Beautiful. If you're interested in Rust and using or contributing to the bindings, check out the VFX RS project on GitHub, and a lot of discussion also happens on the Rust topic on the ASWF Slack channel. Thank you for listening.